So let's go through an example together. We have a point charge that's surrounded by a dielectric spherical shell of epsilon r with an inner radius Ri and an outer radius Ro. We want to calculate the electric flux density, the electric field, the polarization vector, and the potential as a function of r. So the first thing I want to do is draw a diagram. Let's take a look here. We have a point charge, assumedly Q. It's surrounded by a dielectric spherical shell. There's an inner radius and an outer radius. So let's draw two circles. It means we have So that's our dielectric spherical shell. It has a dielectric constant of epsilon r, and it also has an inner radius of Ri, so we call this Ri and Ro. So we're trying to calculate dE, P, and V as a function of r, but if we want to calculate anything as a function of r, it means we have to determine the different regions for r. So let's determine our regions. So we have our first region being inside. Our second region would be within the dielectric shell, and the third region would be outside the whole thing. So we define this as I, and triple I. We have R is less than Ri. For region 2, we have R in between Ri and Ro. And for region 3, we have R is greater than Ro. Just shift this over a little bit. Next, we now take a look at free charges. So we have Q at the origin, so if we were to calculate D, the problem only is a point charge. So okay, so just to recap, we are told that there is a point charge. It's surrounded by a dielectric spherical shell. So the first thing we want to calculate is D. And if we want to calculate D, we can apply Gauss' law. And that's also confirmed because we have a point charge problem. So let's apply Gauss' law. So the next thing we do is just, using this knowledge, we're going to analyze the different regions. And find all of the values that we were asked to find. So due to spherical symmetry, by inspection we expect the vectors E and D to be radial. We can also assume that, or note, that the absolute permittivity is going to be equal to epsilon naught for air. So that means I have epsilon naught on the inside and on the outside. So now let's take a look at the different regions and do our calculations. Region 1 for R is less than Ri. Using Gauss' law to calculate D dotted with ds is equal to Qf. The enclosed charge is simply Q, so I can just set this equal to Q. I'm going to have my electric flux density of the first region, di, times the integral of ds is equal to Q. The surface area of the Gaussian surface that I want to create is that of a sphere, so it's going to have a surface area of 4 pi r squared, that's equal to Q, and I can solve di is equal to Q over 4 pi r squared. This is a vector. We were able to determine that it points out radially by inspection, and therefore this is our answer. So we figured out di. Once we have di, is there an easy way to figure out something else? So we take a look at the equations that we've learned before, and we know that d, or the electric flux density, is equal to epsilon times the electric field in that same region. So I can simply solve for the electric field within that region. So we have di over epsilon r hat. But now I want to take a look at what the absolute permittivity is. And the absolute permittivity in air is simply epsilon naught, that of free space. So we have epsilon, EI is equal to Q, because we can just grab this. It's Q over 4 pi r squared epsilon naught. And that's also in the radial direction. So now I have my electric flux density, my electric field. The last two things I have to solve for are my polarization vector and my potential. So I'm going to leave the potential for you to solve by yourself as practice, but it should come very naturally after you solve for the electric field. So now, to find the polarization vector, we know that P is defined as epsilon minus epsilon naught EI, but we know that epsilon is equal to epsilon naught for region 1. So Pi is simply equal to epsilon naught minus epsilon naught, which is 0, and that is our answer. So you can see how quickly we're working through these questions now. The next region we want to analyze is that between Ri and Ro. Let's start again with Gauss' law. So we have and similarly we have d in the second region multiplied by 4 pi r squared equal to the enclosed charge, which is simply Q. So we note that we have the exact same answer as before. We have q over 4 pi r squared, r hat. Okay, so now we follow the exact same train of thought. We know that d is equal to epsilon e. So the epsilon here is the absolute permittivity of region 2. And we know that for region 2, we have a dielectric constant of epsilon r. So that means we have epsilon r, epsilon naught times E. So I can rewrite this and rearrange this and get the electric field of region 2 as Q over 4 pi epsilon naught epsilon r, r squared, and by inspection, r hat. So we now have our electric field. You can solve for potential yourself, and then we can easily find the polarization vector. Which is epsilon minus epsilon naught, E2, but in this case, epsilon is equal to epsilon naught epsilon r, so we have P2 being equal to, what do we have here? We have epsilon naught, epsilon r minus 1. We're going to replace E2 with what we just solved for here. So we have Q over 4 pi epsilon naught epsilon r, r squared, r hat. We also have P, not also, but we can simplify this down to epsilon r minus 1 times Q divided by 4 pi epsilon r, r squared, r hat. So we've solved for region 2, and now the last region we have to solve for is region 3. So that's when r is greater than RO. We have the integral of d dotted with ds. So we're just going to use Gauss law again. The enclosed charge is always just going to be Q, and the surface area of your sphere is going to be 4 pi r squared. So no matter what, we note that our electric flux density is identical for all three regions. We now take a look at the definition, or the relationship between D and E. So we have D equals to epsilon E. And epsilon here is going to be epsilon naught because it's an air. So it has a dielectric constant of 1. So that means we have E3 being equal to Q over 4 pi epsilon naught r squared, r hat. So try solving for V, and then let's finish this by solving for the polarization vector in region 3. It's going to be epsilon minus epsilon naught, E3, but this is in air, so that means epsilon is equal simply to epsilon naught times 1. So this gives us a polarization vector of 0. And just like that, we've solved for all of the values that we were asked to determine.